time. Thanks to Amazon A9 for hosting us. This is great. So we have a double header today. So first, Ljubomir and Dejan are going to talk about an enhancement they've made to libSVM or SVM Lite, one of the two. And then we have Ted Dunning coming. He's like literally landed at SFO, and he's driving down. So he'll be here hopefully in time. He's going to give a talk about Spark and H2O, I think. So this should be good. So let's start with Ljubomir.
All right, I think I got it. Thanks. Thanks, Arshak. So at this point, I'm supposed to say I'm glad to be here. It turns out to be true, really, because this is my favorite meetup. So that's really the only meetup I think I go to regularly. So it is really an honor to actually give a talk. And I want to thank one more time to Amazon for hosting this. Really nice of them. And Arshak for inviting us. So the subject is libSVM learning, in particular, with particular focus on cross-validation learning and dense data sets. And this here is myself, and my co-speaker is Dejan Miljkovic, right there. So we made a modification to libSVM library, which makes it work faster in certain circumstances, sometimes much faster. And I'll show you the background, the context for this, and then we'll show what exactly he did, because the actual implementation is mostly his work. And I represent a company called Clinical Persona. We do machine learning for life sciences, biotech, pharmaceutical industry, and so companies which have machine learning problems in that particular industry, they contact us if they don't want to deal with this themselves, or don't have the capacity, or don't have the expertise, either way. So they simply decide it's more effective to outsource it. That's our business. And Dejan works for Argyle data, and he also consults for us part-time. So let me just turn this off. So as I said, the subject is faster libSVM library, libSVM software, and probably most of you are familiar with this. And can I just ask how many people have actually used this library? Either is, okay, quite a decent number. Accounting for shy people is probably 2/3. So the subject is basically run a faster version of libSVM. And it has three components or three speedups. One is faster cross-validation. And as you know, at least 2/3 of you, the libSVM can be used to run cross-validation. So I'll explain what is cross-validation and why is it important to improve it, and show a demo how much it was improved. And then two other software architectural or data structure changes, which Dan will talk about. So there are three subjects, really, and then questions and answers. So you could ask why cross-validation, and there are a number of reasons why you could do this. It depends on the industry and the problem you're solving. I'll show the particular context that I work in, and that's called precision medicine. I'll show you in 5 minutes. You'll be an expert, at least, on the concept, what it is. And that concept uses machine learning and genomics and small sample sizes. And when you put all these features together, you pretty soon realize cross-validation is a key component of successfully doing precision medicine, really. And I'll explain how and why. So here's the overall concept of precision medicine. Maybe you listened to President's State of the Union a couple of weeks ago. It was featured there for a couple of sentences, but nevertheless, it's already high profile if it gets there. The concept in principle is really simple. You have a patient, individual there, who comes into a doctor's office and needs treatment, usually for serious diseases. At least at this point, this is applicable to serious illnesses like cancer, cardiovascular events, HIV, that sort of stuff. And the question is, should this person be treated with a particular drug D? And there can be an array of these drugs, and you could ask this question for every single drug. So let's say you have a particular treatment you want to apply. It doesn't have to be drug. It could be radiotherapy or some other treatment. But the question is, should I give treatment to this person or not? And the idea is measure the genome of this individual, then apply machine learning to that genome data, and the machine learning predictor calculates a decision probability, really. That's this P of good outcome or P of bad outcome. I'm sorry, P of good outcome is compared with particular threshold. So if probability of good outcome for this individual on this treatment based on their genomic composition is greater than, say, 80%, then treat with drug D, otherwise try something else. That's all there is to it, really, at the conceptual level. So, of course, there are instruments which measure genome now for, depends, could be couple of $1,000, that ballpark. 15 years ago, it cost $1 billion to do this. Now it's down to a couple of thousand, so it's becoming clinically possible to actually do this in routine care. So the question is then, how do you get this predictor which gives you a probability whether you should treat the person or not? That's a classical machine learning problem. What goes into machine learning is the genome of individuals and their particular outcomes. So you have for each training set patient, you have a set of measurements, and that set could be from a couple of several measurements, handful, to millions to billions. Depends on how much of the genome you actually measure. But it doesn't matter. The point is you get a vector for each individual. And you get outcome for that individual, good or bad. And with that setup, this becomes a classic machine learning problem. You have to predict, given the genome, what is going to be the outcome. And that's what goes into this learning, and that's what becomes a best model or predictor. In this field, a model is called a signature. That's just the terminology that they use, or we use. So if you look at projection of one particular problem of precision medicine in 2 dimensions, let's say you measure just 2 genes, 1 and 2. The blue is good outcome, the red is bad outcome, and the task is relatively straightforward. Find a classifier which will separate this into 2 groups most accurately. And then in clinical care, you apply this classifier and it tells you what's the probability of good outcome for any given incoming patient. So is this clear so far? Or? Okay, a couple of notes might be good. So then the question is, how do you prove once you built your classifier that it actually works? For that you need to run independent clinical trial. You have fixed classifier which predicts outcome, and you have, that was built using this box here. You already seen this. This is a classic machine learning stuff. And then you apply this to a previously unseen population of patients whose genomes you have measured and whose outcomes are known but hidden. You apply this classifier to this population, and then you compare the predicted outcomes and the real outcomes. Again, classic machine learning validation setup. And if the match is pretty good, the test passes, it goes to clinic. If it doesn't, that's the end of it. In this context, if you fail, this usually means either the end of the company or at the very least end of that department, because that's how it is. You only get one chance. Getting another population and retraining, that's in clinical and practical terms usually not possible. So there is your one chance to get it right. So having been there a couple of times, it can be a pretty tense moment. But eventually, at least some of these tests do pass and get used in clinic. So we'll get to libSVM momentarily. So hang in there in 5 minutes. The connection will become kind of trivially obvious. So when you put all this stuff together, which is precision medicine, machine learning, these samples here are usually very small. Just to give you an idea, this is a real sample which has about 130 or 50 patients, and it takes years sometimes to collect this because you have to follow them for their actual outcome. You have to know how well they responded to treatment or how long they actually lived. So each point here is actually a human life, and in particular in cancer, each point there means life or death for an individual. So it's extremely hard to collect this data. Therefore, the sample sizes are very limited. Hundreds, that's pretty large, sometimes less than 100. Thousands, that's almost enormous, hardly ever seen. So bottom line is you have to use as much information out of this limited population as possible. So how do you do that? The conclusion is you have to do a lot of cross-validation learning. In other disciplines where you have thousands, or I don't know, in movie recommendations, maybe you have even millions of points, then you don't really need to do this because you have enough data for independent validation of your models. But here, you have to use every single point very thoughtfully. That leads to cross-validation, and the more cross-validation you can do, the more reliable your conclusion will be. So I have this cross-validation law, as I call it, which basically says cross-validation, magnitude of cross-validation is inversely proportional exponentially to the sample size. Meaning if you have a lot of samples, you don't need to do cross-validation, or maybe only something. So let me just start now that to do cross-validation, Dan and I made a change to libSVM library, which was actually presented in this forum by CJ Lin a couple of months ago. Maybe you attended. It was a great talk. So Dan took this library and noticed that in cross-validation mode in particular, and in some other instances, it is not as efficient as it could be. So at this point, I'll start a little demo, which hopefully will show the difference in performance between these two softwares. So basically what Dan and I did was create a libSVM, or libSVM, I never figured how to pronounce this correctly, but libSVM clone, which is called cross-SVM, that's executing on the right side of the screen. And on the left side is the very standard libSVM version 3.17, which is just 3 minor releases behind. And it's executing a 10-fold cross-validation. You can see the command line here. Those of you who use cross-validation will recognize this -V10. That's a tenfold cross-validation on a particular genomic data set. And the changes Dan will describe what's the content of the changes in cross-SVM. But in principle, it is totally backward compatible. All you need to do is add one more little flag to say turn on fast mode. Basically, that's what it takes to run this. So if you take a look on the right, that's the fast one. It took 37 seconds, give or take. This will run exact same processing. They produce absolutely identical results. I'll let it run, but to give you a heads up, I'll go to a couple of slides, and it still won't be finished. So now back to these slides. Of course, there is some price to pay if you there's no free lunch. So the first price is that the kernel matrix, which is the matrix of scalar products of all samples in the data set, it must fit in RAM. So in our applications, which are clinical, as I explained, the typical data sets are hundreds to thousands. The biggest one I've seen was about 3,000 patients. So needless to say, this is not a restriction at all. 3,000 by 3,000 easily fits into RAM. For huge big data problems, it is a restriction. This could handle, I don't know, maybe we did try 500,000. Maybe you can fit 1 million, something like that. But if you have billions of samples, this is out of the question. Nevertheless, there are a lot of areas where you don't have that many data, so then you can use this. And second limitation is this cannot, at least the cross-validation part doesn't work with feature selection. That's because each subset of features is a different, produces a different kernel matrix, and the key innovation here is reusing the kernel matrix. But if you select features, each subsequent subset of features is a different kernel matrix. There is no reuse, it's out of the question. And nevertheless, if you don't do this, you can benefit from this improvement. So that's the cross-validation part. Let me see if there is some progress here, but it'll run for a few more minutes. So at this point, let me just show you briefly while it's crunching. The actual applications of this do exist today. They are relatively, by this I mean precision medicine. They are relatively limited. I have two examples here. One is called Oncotype DX breast cancer test, and it gives a probability of recurrence of breast cancer after initial surgery. And why this matters? It matters because if the cancer recurs, it's basically deadly. There's no cure for recurrent cancer. But you can reduce the chance of it coming if you administer chemotherapy. But chemotherapy, as you know, is basically poisoning, and people would rather avoid it if there is no chance of cancer recurring. Bottom line, it's important to know what's the chance of recurrence for every patient. And this test gives them. This is the chance of recurrence. In this particular patient, it's about under 10%. So it's reasonable to assume there is no need to apply toxic treatment to this individual. So this is a very widely used test. It's basically standard practice in United States and a couple of other countries. This test is another example. I worked on this for 9 years, and it's a test which determines the actual origin of cancer. So for a given tumor, it reads the genome and then does the machine learning, and it produces 15 probabilities which tell you what's the type of the cancer that the patient has. And in this particular case, you see that the ovarian cancer stands out, so the diagnosis is probably that. And this test uses, so since I worked on this, I know what's behind. It uses support vector machine. It was developed, I would say, almost exclusively using cross-validation. Not in a straightforward way, but nevertheless, the basis for this test development was cross-validation. And it used the linear SVM curve. And it was heavily validated in clinical use. In fact, we had a kind of competition between this test and human pathologists for diagnosing cancer, and they came out approximately equal. This one was slightly better. So there is clinical use for this. It's getting more widespread, but at this point it's still somewhat limited. Let's see the still crunching. So I think I'll leave it as this. And now it's, I'll give this back to Dan to explain what's the Okay.
Yeah.
I'll stick around until this finishes.
Okay, yeah, I need an assistant. Thank you, Ljubomir. Thank you for coming, and one more time, thank you to, for A9 to organizing this event. And yes. Okay, cross-validation implementation. So what happened is basically, Ljubomir, how this collaboration started is there was a competition, and basically that data set was really big, and basically using the libSVM was impossible. It would take days to do one experiment. So we started looking into it, well, what's going on there, and we figure out basically that the implementation is done in a sense that it takes, basically it's a global, it's general library, so it needs to cover the lowest common denominator, which is sparse matrix.
Add 2 words. Just add 2 words.
Mm-hmm.
This data set was big in terms of features.
Yes.
Because they measured a couple of million genomic features. But the number of patients was around 1,000.
1,500. Around 1,000. So basically we call that.
Is a training set. Just to make that clear.
Yes, we call this problem short and wide, basically. So what happened is we started looking into the library and figure out that basically the libSVM is calculating, spending plus 90% of the time in doing the dot product function, and basically that this is for every calculation, it starts everything from the beginning. Basically there is no remembering. So if you're a software engineer, if you can calculate something once and remember, do that. So that's super important feature. So we started digging into it and trying to figure out how we can improve this and possibly remember that. Can we see if it is done or?
Yeah.
Yes, great.
Yeah.
Excuse me. So you can see the pride and joy. So this is like half a minute versus 9 minutes, which is what 9 by 2, 18 times faster. So if you need to do a lot of this, it makes a huge difference. And for Ljubomir, basically, in order to manage these experiments, his company was using Amazon Cluster. You can launch many machines, but that costs money. So by this, you can just reduce your spend on Amazon by 20 times. What normally happens is your demands then are bigger, so but still you can do the stuff there. So yes. And also this other 2 improvements which were added is basically dense matrix handling. libSVM assumes that everything is in a sparse matrix. That's a general case, so they cover that case. And then one more also important feature is data locality. If you're doing math in the computer science, when you multiply matrices and everything, be careful, super important how your language column wise oriented or row wise, how the data is stored in every language is a little bit different. Java is column. One of these, it's easy. C and Fortran is different, and many of these libraries are first developed in the Fortran and then ported to Java. So I have one example just by transposing matrix in Java for the code which was ported. We got a 5 times improvement in the speed. So very, very important stuff.
The speed improvement you got in Java, is it related to Fortran or C?
No, this is you mean for this particular one? Yeah, this is a C Java port basically.
From which language?
Java to Java.
Java.
To Java. Okay. So let's do another one. So let's go back to the first improvement and how we started the whole game is this cross-validation. So this is our short and wide data set. That's a full learning set. So what is happening when you're doing the whole thing, you create a kernel matrix. And this basically is the number of experiments. In our case is number of patients. And this side is basically how many features you have. Meaning if you're looking to genomic data, in that set was 1.5 million. So basically this matrix reduced to the n by n. And what is very interesting also, this matrix also is symmetric. So basically you need to make just, well, this is missing, but anyway, n squared half, more or less, dot products. What libsvm does is, if you're doing a cross-validation, it creates this whole kernel matrix every time. So the idea is why we don't reuse this matrix. So now, when you're doing a cross-validation, basically you take a portion of the data, we call it validation set, and the rest is the excuse me, learning set. Normally, we do the tenfold cross-validation, which means you take 10% of the data from each side. And that means that for one cross-validation, libsvm it would make 0.8 n squared dot products. Now, but if you look at this, basically this kernel matrix, if you calculate once everything, that's it. You can reuse stuff. So the total number of dot products which standard libsvm is using is 8 times n squared. N squared is number of patients. If we reuse the data, we just need to do n squared half approximately, which give us 16 times less dot product. So that's a huge thing, basically. You get, of course, you have some overhead when you're doing reuse, but just implementing this simple trick, you can possibly get 10 to 15 times improvement in the speed, which is a huge thing. Yes. Okay, now we started digging into the code, how to implement that. And the libsvm is, because in order to handle the sparse case, they created a class which represents one data point, which is the value and index. And then, because you need a matrix, basically the data is stored as a matrix of objects. This is a super bad idea in math, if you're doing math, because you don't have so-called this data locality. Objects are stored anywhere in the memory, and if this matrix, pointers to the objects here next to each other, but when you want to grab the data, they are all over the place. So basically, you are losing the performance. What we decided to do is, why care? We are going to store everything in one matrix, and this perfectly works if you have a dense data set. So in this case, in Ljubomir's case, it was really full data set. There are no zero elements. But it's also beneficial to represent as a dense data set, even if you have, say, 70% non-zero values. Still you get a performance benefit. Also, by storing data this way, we reduce memory, so we can put a lot of data more inside because we lose this overhead of class. So this basically way of storing the data save us maybe 30 to 40%. So you can put an even bigger data set. And this feature basically added, on average, 2 times speed improvement just by having this data locality. So even if you don't do the cross-validation, you're going to get benefit if your data set is, if you use this feature. Okay, next one. Now, if you remember, we need to also handle the sparse data sets. So we said, okay, fine, we'll reuse basically this data and store not value, but we'll store next to each other index value. We'll use the same matrix to store indices of each value and the value itself. Nothing prevents us to do that, right? The other standard implementation is when you're dealing with a sparse data set is to have a matrix of values and matrix of indices. I thought to implement that, but this was easier because less changes needed in the code, basically. You just change this and that's it. Everything is handled by code already. If I added another matrix, I would need to put everywhere another matrix, more testing, and all this stuff. So basically also, which means that, see, this matrix, we have a sparse data set and full data set. You need to tell to the libsvm, my data is sparse or full. You'll see at the end we added 2 flags. One is the matrix is full. You want your data to be treated as a full or sparse. Excuse me. And the other flag is use this fast cross-validation, which is remembering the data. This, okay, next slide, sorry. Now, this is also accept of the code. This is original libsvm implementation. Because we always take care of if this matrix is, we assume that the data is sparse, we need to have these ifs to check if 2 indices of a data are the same, right? So for every calculation, every time we need to do this. If we have a full data set, basically this is a cross-SVM implementation. We say, okay, is this problem sparse or full? If it is a full, basically just in your dot product call, problem is a full, call the full implementation of the dot product. Boom, no if, right? So, and I said plus 90% of the time in libsvm is spent in this dot product function. If you remove couple ifs and everything, you gain tremendously. So on dense data sets, if you're using libsvm, our implementation cross SVM, you're gonna get another double in speed. So if you are still not using the cross validation, you're gonna get 3 to 5 times speed improvement on full data sets. If your data set is sparse, you're gonna get around 2 times improvement just by changing the data structure. So no matter what, use cross SVM.
I have a demo for this. Do you want to?
Maybe later. Let's finish the. And now basically this is the improvements in speed among different data sets we got. So this is how many meaning times improvement. On the top of the bar this is a basically full data set. How full is the data set? And if you can see, if data sets are kind of sparse, you don't get much, but still you get a lot. But on average, on full data sets, you get 20 to 30 times speed improvement, which is a really, really big deal, especially in a case when you have this cross-validation. Normally, you need to do thousands of cross-validations to pull the best out of your data. you save a lot of time. Now, this is a comparison between cross SVM and liblinear. So there is like saying the liblinear is always faster than libSVM. Not true, meaning liblinear is green. So yes, in some cases it's faster, in some cases it's not. So basically this cross SVM can compete with liblinear also for the linear kernel. And do we have anything else? Nope. Okay, yes. As I mentioned, there are just 2 flags added to this library. Everything is the same user, absolutely everything. We preserve everything. You need to just say, is this a problem sparse or full? Default is sparse, so basically you just run this one, no problem. And then there is a U flag is reuse. This is meaning if you want to reuse data in a cross-validation. So that's it. And you have what do you want to?
I just want to show the comparison and performance when you don't use the cross-validation. So the bulk of the talk was about cross-validation scenario, but Dan explained there are additional improvements in the cross-SVM. So that's what I want to run.
Okay, demo. Okay.
This is the on the left is just regular libSVM, no cross-validation, and it's using linear kernel. Probably recognize that, and that's it. On the right-hand side,
yeah, we have this f minus f1, so that's
You can maybe explain.
Yeah, so same thing basically what we said. You just add the flag f1. We are saying this is a full data set, and yes, we got what point? Okay, cool. 28 seconds. I don't know how long the other one is gonna be, but
it's about 2.5 times. Yeah, 3 times.
So that's it. Let's go to the last slide. It's
let this run.
Let this run. Okay.
We can go over to questions.
Yes.
Actually, why don't we start questions while this is running?
Yeah. Please, any questions?
Yeah.
Sure.
I had a question about the precision medicine application where you were showing prediction, some probabilities. How were you getting the probabilities reliably out of SVMs?
Good question. So, I mean, you can use the plots probability approximation. That's the first starting point. And then when you have a validation study, you can compute something called Hammer-Lemesher curve, which basically measures the calibration strength of your computed probabilities. And then you come up, based on this analysis, you come up with that curve you saw with the Oncotype DX. That's how it was done. So they don't even produce probabilities. They produce this arbitrary recurrence score, and then they adjust those scores such that the particular regions, intervals in that score correspond to actual probabilities they recorded in a relatively large validation trial.
Okay,
So that's how.
It's just done through calibration.
Yes, yeah. It's not perfect, but it's shown to be useful. That's short answer.
And just to, sorry, so we got almost three times improvement. So one more time, use cross SVM.
This is as close to free lunch as possible.
Yeah, there is nothing there. Basically, we don't reuse nothing. You can process any data set. You're gonna get something. So.
We put up the GitHub URL.
Yes.
In case somebody wants
Another
to
question about the precision medicine. So in the graph where you had the good and bad results, I was wondering, I might have missed what that was actually measuring, but a lot of results of drugs are not 0 or 1, right? they're continuous values, or they have different labels. So can you talk a little bit more about that?
Sure. There is a simplification for the purpose of fitting this talk into reasonable time. But in reality, it depends on a disease. In cancer, which is most of the experiences in cancer, you generally measure survival, simply in months or years, hopefully, and you run a regression which estimates survival, not black and white. Now and then for the purpose of demonstrating performance, generally you report how accurate you are predicting probability of survival, let's say 5 years or 10 years. But that's just for the purpose of telling people this is how accurate the test is. Does that make sense?
Yeah, and just one follow-up question. So, in case of cancer, even if you're looking at one type of cancer, part of cancer's genomic impact is that it's very different than many different subtypes of cancer. So, how did you find that effect, in particular for cancer, when you're looking at features that are the sequences?
I'm not sure I understood. Dejan asked me to answer the question. Can
Maybe we gotta wrap it up here. Thank you, guys.